Imagine standing on Mars after the engines have gone quiet. The dust is still falling around the landing site. The sky is not blue. It is a thin, rusty haze, and the sun above you looks smaller than it should. Behind you is the habitat that has to keep you alive. In front of you is an entire planet that no human has ever walked on before. For a few minutes, it would feel like the greatest achievement in history. Then, the first terrifying question would arrive. How do you get back? That is the part many people imagine too quickly. We picture the first Mars crew planting a flag, collecting rocks, waving at a camera, and eventually launching home when the mission is finished. But Mars is not a campsite. It is not a distant version of the Moon. It is a planet with gravity, weather, dust, seasons, distance, radiation, and a sky that can hide the sun for weeks. Getting there would be one impossible problem. Leaving again may be the harder one. Before we begin tonight's journey, make sure you subscribe to the channel. Leave a like if you enjoy calm space documentaries, and write in the comments where you are watching from and what time it is right now where you live. It is always strange to imagine people all over Earth watching the same universe from different places, under different skies, at different hours of the night. Tonight, you are watching the Just About Space channel, talking about why the first humans on Mars may be trapped forever. And to understand why, we have to begin with something that sounds simple, but is not simple at all. A mission to Mars is not one journey. It is a chain. Every part of that chain has to work in the correct order at the correct time, after months of flight, across millions of kilometers of empty space. The launch from Earth has to work. The cruise to Mars has to work. The entry into the Martian atmosphere has to work. The descent system has to slow down a heavy spacecraft in a thin atmosphere that is not thick enough to behave like Earth, but not empty enough to ignore. The landing legs, engines, navigation, heat shield, communication system, power system, surface habitat, life support, suits, rovers, oxygen reserves, water systems, food storage, medical supplies, and return vehicle all have to survive. But even after all of that, the crew is not safe. They have only arrived. The return home requires a second miracle. A rocket has to lift off from another planet, climb out of Martian gravity, reach orbit, meet the spacecraft waiting above Mars, transfer the crew, survive the return cruise, and bring them back to Earth after a mission that may have lasted years. If any one link in that return chain fails, Mars stops being a destination. It becomes a prison. The frightening part is that the prison does not need walls. It does not need guards. It does not need a lock. It only needs distance, physics, and one broken system that cannot be replaced. On Earth, rescue is part of how humans survive. If a ship breaks in the ocean, another ship can be sent. If a climber is trapped on a mountain, helicopters may try to reach them. If a building collapses, people can dig through the rubble. Even in Antarctica, one of the most isolated places on Earth, rescue can sometimes be planned with aircraft, ships, and weeks of effort. Mars changes the meaning of rescue. When Earth and Mars are close, they are still tens of millions of kilometers apart. When they are far apart, the distance can be several times greater. A radio signal takes minutes to cross that space one way, and the planets are always moving. There is no emergency spacecraft waiting nearby. There is no quick launch window whenever something goes wrong. There is no simple path where Earth can aim a rocket and send help like a lifeboat. The first crew would not simply be far from home. They would be separated from home by orbital mechanics. That phrase sounds calm, almost technical, but it is one of the most merciless ideas in spaceflight. Planets do not wait. Earth and Mars move around the Sun at different speeds. A mission cannot just leave whenever it wants and return whenever it wants without paying an enormous cost in fuel. There are windows, alignments, transfer paths, and energy limits. The crew might be able to walk outside on Mars and see Earth shining as a bright point in the sky, but that does not mean Earth is reachable. The door home may only open at certain times. If the return vehicle is not ready when that time comes, the crew may have to wait for the next opportunity. If the life support cannot support that extra weight, the mission becomes a countdown. If a medical emergency happens after the departure window closes, there may be no way to leave quickly enough. If a dust storm damages power systems during the final months, the crew may not be fighting for comfort. They may be fighting to keep the return plan alive. This is why the first humans on Mars may not be trapped by one dramatic disaster. They may be trapped by delay, a valve that does not open, a pump that loses pressure, a computer that refuses to boot, a seal that leaks too slowly to look urgent at first, a tank that produced less oxygen than expected, a storm that arrives during the wrong week, a part that would be easy to replace on Earth, but is now lying in a warehouse, millions of kilometers away. Mars would not need to destroy the mission all at once. It could simply make one needed thing unavailable at the wrong moment. That is the first terrifying problem. The second is that the return trip may have to begin before the astronauts ever arrive. A safe Mars mission would likely need cargo sent ahead of the crew. The habitat, supplies, power systems, and ascent vehicle could be pre-positioned on the surface or in orbit. The reason is not just convenience. It is survival. You would not want astronauts to land on Mars and then discover that their return rocket still had to be built, fueled, checked, and trusted from scratch. In many serious mission concepts, the crew should not even leave Earth until key systems on Mars have already landed and proven they can operate. The return vehicle may need to be waiting. The power source may need to be running. The machines that produce oxygen or propellant may need to have filled the tanks. The habitat may need to be healthy. The landing site may need to be confirmed. The communications system may need to work. This makes Mars feel less like exploration and more like an enormous remote construction project. The first humans would not be stepping onto a planet as pure pioneers with only courage and flags. They would be entering a field of machines that had to arrive earlier, unfold correctly, anchor themselves, start producing resources, and survive alone for months or years before the crew trusted their lives to them. And those machines would be doing this on Mars, a planet with cold nights, dust-covered surfaces, electrical charging, rough terrain, thin air, unpredictable storms, and no technicians walking over with a toolbox. On Earth, when a fuel plant fails, people investigate. They walk around it, they listen for sounds, they feel vibrations, they replace parts, they bring in experts, they order components, they run tests. They can stand next to the machine and understand it with their senses. On Mars, a broken propellant plant may be a silent metal box under a red sky. If it stops working before the crew launches from Earth, the mission can be delayed. That is frustrating, but survivable. If it stops working after the crew has already landed, the meaning changes. The entire planet becomes a waiting room. The reason propellant matters so much is simple. Rockets are not magic elevators. To leave Mars, the crew needs fuel and oxidizer. Mars has less gravity than Earth, but it still has enough gravity to make escape difficult. A spacecraft that lands on Mars cannot casually hop back into orbit, like a small aircraft leaving a runway. It has to launch, accelerate, steer, survive vibrations, and reach the correct orbit with extreme precision. Every kilogram matters. If all the return propellant has to be carried from Earth, the mission becomes heavier before it even begins. More mass means larger rockets, more launches, more cost, more complexity, and more things that can fail. This is why making resources on Mars is so tempting. Mars has an atmosphere rich in carbon dioxide. In theory, machines can use local material to make oxygen. That oxygen could help astronauts breathe. But for return, it may be even more important as oxidizer for rocket propellant. That idea is powerful. It is also frightening, because now the path home depends on a factory operating on another planet. A small technology demonstration can prove that oxygen can be made from Martian CO2. But supporting a human return mission is not a small demonstration. It means industrial quantities. It means reliability. It means storage. It means valves, compressors, filters, heaters, cooling systems, sensors, tanks, seals, software, power management, and months of operation in an environment that never becomes friendly. A future crew may look at a tank gauge and know that their survival depends on the numbers rising. Not a speech, not a dream. A number, enough oxygen for ascent, enough pressure in the tanks, enough power to keep production running, enough time before the departure window. That is a very different kind of drama from the one we usually imagine. It is not the drama of a monster, an explosion, or a single heroic moment. It is the drama of slow engineering. It is watching equipment do exactly what it must do, day after day, with no applause. Because one day 6 people may climb into a vehicle and trust that machine with their way home. If the plant underproduces by a small amount, the crew may have to wait. If the tanks leak, they may have to repair them. If the power system fails, the plant may stop. If dust blocks a radiator, overheats equipment, or coats solar arrays, production may slow. If the oxygen is contaminated or the system cannot certify the quality, the rocket may not be safe to launch. And if the launch cannot happen when Earth and Mars are aligned, the crew may not be delayed by hours. They may be delayed by years. This is where the story of being trapped begins to feel realistic. Not because Mars has some mysterious force pulling humans down. Not because astronauts would be helpless. They would be highly trained, carefully selected, and surrounded by the best technology their civilization could send. But the margin for error would be thin. A Mars return mission is not just a question of whether humans can survive Mars. It is a question of whether they can keep a return system alive long enough for the sky to open in the correct direction. And that depends on power. Power is the hidden heartbeat of every off-world settlement. It is not as dramatic as a rocket launch, but without it, everything stops. The lights go dark. Air stops circulating. Water stops being purified. Carbon dioxide removal slows. Computers shut down. Heaters fail. Food production collapses. Communications weaken. Scientific work ends. Repairs become harder. The habitat stops being a home and becomes a metal shell, losing the fight against the planet around it. Mars receives less sunlight than Earth. Solar panels can still work there, and robotic missions have used them successfully. But a crewed mission is not a small rover. It is a living system. It needs power during the day, at night, during cold periods, during storms, during equipment failures, and while producing return resources. The problem is not only darkness, it is dust. Mars is famous for dust storms, and some can grow large enough to cover huge regions of the planet. Dust, suspended in the atmosphere, can reduce sunlight. Dust settling on panels can reduce efficiency. Dust entering mechanisms can cause wear. Dust coating surfaces can change heating and cooling behavior. Dust is not just a color in the landscape. It is a slow attack on systems that need clean surfaces, moving parts, sensors, seals, and stable temperatures. For a robotic rover, a long dust storm can be dangerous. For a human base, it can be existential. A storm that reduces solar power at the wrong time could force the crew to conserve energy. Conservation sounds manageable until you list what energy means. Heating the habitat, running oxygen systems, recycling water, preserving food, maintaining computers, charging rovers, operating medical equipment, producing propellant, keeping batteries healthy, communicating with Earth, preventing pipes from freezing, keeping suits ready, managing emergency systems. If power has to be rationed, the mission has to choose priorities. And when the return vehicle depends on ongoing production or maintenance, power shortage becomes more than discomfort. It becomes a threat to escape. This is why many serious Mars plans consider nuclear fission power. A reactor does not care whether dust is in the sky. It does not need sunlight. It can provide steady power through night and storms. But that creates another chain of risks. The reactor must be launched safely, landed safely, deployed safely, operated safely, cooled correctly, shielded properly, and connected to the rest of the base. It must survive the trip. It must not fail at the moment when every other system is depending on it. On Earth, power grids are vast and redundant. If one station fails, others can often help. If one cable is damaged, crews can repair it. If a generator breaks, replacement parts can arrive by truck. On Mars, the power system may be a few machines on an empty plane, a cable buried in dust, a reactor placed away from the habitat, a field of solar panels slowly losing brightness under red powder, a battery bank that has to carry the base through a bad night. The first humans on Mars may not be trapped by a dramatic engine failure. They may be trapped because the machines that keep the return system alive lose power slowly, and every repair consumes time, oxygen, crew strength, spare parts, and risk. That is what makes Mars different from most exploration stories. On Earth, an explorer fights nature, but still exists inside Earth's support system. The air is breathable. The pressure is survivable. Rain falls from the sky. The planet itself is not trying to freeze your blood or dry your lungs in seconds. Mars does not offer that background mercy. Its atmosphere is thin, mostly carbon dioxide, and far too weak to protect humans the way Earth's atmosphere does. It cannot provide breathable air. It does not keep surface temperatures stable. It does not shield the surface well from radiation. It does not stop small objects from reaching the ground as effectively as Earth's thicker air. It is an atmosphere only in the technical sense, not in the comforting sense. If a habitat loses pressure on Mars, the crew cannot step outside and breathe. If a suit fails, there is no backup atmosphere around the person. If a rover breaks far from base, the crew is not stranded in a desert. They are stranded inside an environment where the entire planet outside the cabin is incompatible with the human body. This is why every activity on Mars would be tied to vehicles, suits, alarms, checklists, and return routes. A simple field trip to collect samples becomes a life support operation. A drive across a valley becomes a calculation of oxygen, battery capacity, suit integrity, communication range, terrain risk, and the ability to get back if one rover fails. Every footprint outside the habitat would carry a question behind it. Can you return from where you are standing? That question applies to the entire mission. The astronauts may be physically standing on Mars, but psychologically, they would be measuring everything against the path home. The lander, the ascent vehicle, the propellant tanks, the power system, the spare parts, the medical condition of the crew, the launch window, and the weather would all form one invisible map. If that map breaks, Mars gets larger. A base only a few hundred meters away can become unreachable if a suit fails. A return rocket only a short walk from the habitat can become useless if its systems cannot be verified. Earth can be visible as a point in the sky and still be unreachable in practice. Distance is not the only thing that traps people. Dependency traps people. A human on Mars depends on a sealed chain of technology. Air depends on pumps and scrubbers. Warmth depends on heaters and insulation. Water depends on recycling and storage. Food depends on supplies or controlled growth systems. Mobility depends on suits and rovers. Communication depends on antennas, orbiters, power, and alignment. Return depends on the ascent vehicle, propellant, orbit, timing, health, and the spacecraft waiting above. The terrifying part is not that all of these systems are impossible. The terrifying part is that all of them are necessary. A submarine also depends on technology, but it can surface. An aircraft also depends on engineering, but it can land. A space station depends on life support, but spacecraft from Earth can visit it comparatively quickly. Mars is different because it combines a hostile environment with a rescue distance so huge that failure becomes a local problem. The crew has to solve it where they are. This creates another danger that is easy to overlook. Mars forces repairs to become survival. The first crews would need to be scientists, pilots, doctors, engineers, technicians, electricians, mechanics, farmers, programmers, and emergency responders. All at once. They would need to diagnose systems under pressure, with Earth delayed by signal travel time. Ground control could help, but it could not guide every movement in real time. If something starts leaking, burning, freezing, jamming, or failing, the people on Mars have to act first. And repair on Mars is not like repair inside a workshop. It may happen in gloves thick enough to reduce touch. It may happen while wearing a pressurized suit that makes every movement harder. It may happen during cold, dust, limited visibility, low light, or after hours of preparation. It may happen with only the parts already available. It may happen while the crew knows that if they damage one more thing, the situation becomes worse. A broken connector on Earth can be annoying. A broken connector on Mars can disable a pump that keeps water moving. A stripped bolt can delay access to a critical compartment. A cracked hose can mean lost pressure. A sensor fault can make a safe rocket look unsafe, or a dangerous rocket look acceptable. Even uncertainty becomes dangerous because launching from Mars with an unverified system may be as deadly as not launching at all. Before the first humans can return from Mars, they have to trust the ascent vehicle. Trust is not a feeling in this case. It is data, tank pressure, valve response, battery health, engine readiness, software status, structural integrity, guidance system alignment, thermal control, communication with orbit, emergency abort options, crew health, weather, time. If any of those indicators refuse to cooperate, the crew may have to decide whether to launch anyway, wait, repair, or accept that the return plan has changed. None of those choices is simple. Launching with a questionable system may kill everyone during ascent. Waiting may consume supplies. Repair may expose the crew to danger. Accepting delay may push them beyond the planned mission duration. The return from Mars is not just another launch. It is the moment when the planet tests every assumption humans made before they came. To reach that moment, the crew must first survive landing. Landing on Mars is one of the strangest problems in planetary exploration. The atmosphere is thick enough to heat a spacecraft violently during entry, but too thin to slow a heavy vehicle easily with parachutes alone. Robotic landers have used heat shields, parachutes, retro rockets, airbags, sky cranes, and careful navigation. Human missions would be far heavier. A habitat, supplies, ascent vehicle, and crew lander are not small machines. This matters because the trap can begin before the crew ever steps outside. If the landing is off target, the crew may be far from pre-deployed supplies. If the descent damages the vehicle, the ascent system may be compromised. If engines blast dust and rocks across the landing site, nearby equipment may be coated or damaged. If the lander tips, sinks, cracks a line, or settles unevenly, the mission may begin with emergency repairs. A landing that is survivable can still be mission-ending. That is a frightening category. Not death, not success, but a wounded arrival. The crew is alive. The cameras show cheers on Earth. The first step may still happen. But somewhere below the public celebration, engineers notice a reading that should not be there. A pressure drop, a bent strut, a communication glitch, a valve position that does not match the command, a dust-covered radiator, a damaged antenna. Mars can turn victory into triage. This is why the first few sols would be some of the most important days in human history. A sol is a Martian day, slightly longer than an Earth day. During those first sols, the crew would not be living the romantic version of exploration. They would be checking, testing, inspecting, securing, connecting, and comparing reality with the plan. Is the habitat sealed? Is power stable? Are the supplies accessible? Can the suits operate? Can the rover move? Can the crew communicate? Is the ascent vehicle healthy? Can the base survive the first night? A human Mars mission may become famous for the first footprint, but the quieter tests may matter more. History remembers flags. Survival remembers checklists. Mars at night would not care about either. The temperature can fall brutally. The thin atmosphere does not hold warmth well. Equipment has to be designed for thermal cycling, with materials expanding and contracting, batteries losing performance in the cold, lubricants behaving differently, seals becoming stressed, and electronics needing careful temperature control. A person inside a habitat may be warm, but the habitat is working to create that warmth every moment. That is easy to forget. On Earth, warmth can feel natural. Buildings leak heat, but the outside environment still belongs to the same planet that made us. On Mars, warmth is manufactured, pressure is manufactured, breathable air is manufactured, drinkable water is managed, safe movement is manufactured. The first humans on Mars would live inside an artificial bubble. If the bubble remains healthy, Mars becomes a workplace. If the bubble weakens, Mars becomes a threat. And the bubble has to remain healthy for a long time. A trip to Mars is not a weekend expedition. Depending on the mission plan, the crew could spend months traveling there, many months on the surface, and months returning home. Some long-stay mission concepts place crews on the surface for well over a year because waiting for better planetary alignment can be more efficient than trying to rush back quickly. That means the first humans may not simply visit Mars. They may have to live through seasons, dust cycles, equipment aging, crew fatigue, routine maintenance, and the psychological shift from mission excitement to ordinary survival. At the beginning, every sound in the habitat would feel historic. The hum of fans, the clicks of instruments, the muffled movement of suited astronauts entering an airlock. The first meal, the first message from Earth after landing. But after weeks and months, those same sounds may become the background of confinement. The crew may wake up and see the same walls, the same red landscape, the same schedule, the same warnings, the same distance from home. Outside the window, nothing is alive. No trees move, no birds cross the sky, no ocean reflects light. No clouds gather like Earth's clouds. The landscape may be beautiful, but beauty does not make it welcoming. The human mind is part of the mission hardware. If the crew loses focus, systems suffer. If conflict grows, decisions suffer. If sleep breaks down, judgment weakens. If homesickness becomes severe, morale drops. If someone becomes depressed, anxious, angry, or reckless, Mars has no spare crew waiting nearby. The group is the rescue team, the maintenance team, the science team, and the family system, all at once. A return mission depends on their bodies. It also depends on their minds. This is another way Mars could trap people without touching the rocket. If crew performance declines, Maintenance may fall behind. Small problems may not be noticed early. Risky choices may be made. Communication with Earth may become strained. People may avoid conflict until it becomes dangerous, or argue over priorities at exactly the moment when unity matters. On a normal expedition, a struggling person can sometimes be evacuated. On Mars, evacuation is the mission, and the mission may not be ready to evacuate anyone. Medical emergencies become especially frightening. A broken bone, kidney stone, infection, dental abscess, appendicitis, allergic reaction, suit injury, radiation sickness, or psychological crisis could become far more serious than it would on Earth. The crew would carry medical supplies and training, but they cannot bring an entire hospital. They cannot call an ambulance. They cannot receive real-time surgery guidance without communication delays. They may not have the right specialist, the right instrument, or the right medication for a rare event. A medical problem also affects the return plan. Can an injured astronaut climb into the ascent vehicle? Can they tolerate launch forces? Can they function during rendezvous? Can the crew care for them during the journey back? Does treating them consume supplies needed by everyone? If one person becomes too sick to launch, does the crew leave them? That last question is almost unbearable. But Mars mission planners cannot ignore ugly questions simply because they are painful. A place that cannot be reached quickly forces moral decisions into engineering plans. If the return vehicle has a narrow launch window and one crew member cannot be moved, the mission becomes more than a technical emergency. It becomes a human crisis with no clean answer. This is what people mean when they say Mars could become a one-way trip. It is not always because the mission was designed to be one-way. It is because Mars creates situations where return requires everything to remain inside limits. Health inside limits. Fuel inside limits. Power inside limits. Hardware inside limits. Time inside limits. Crew cooperation inside limits. Once enough of those limits are crossed, the return can disappear gradually. The astronauts may still be alive. The habitat may still function. The mission may still send messages. But the path home may have closed. That possibility becomes even darker when we consider radiation. Earth protects us with a thick atmosphere and a global magnetic field. Mars does not have that kind of global shield today. On the surface, astronauts would face galactic cosmic rays and bursts of solar energetic particles from solar storms. Shielding can help. Habitats can be covered with regolith. Storm shelters can be built with water, supplies, or dense material around them. Mission timing can reduce some risks. Monitoring can warn crews when solar activity is rising. But radiation is not a dramatic villain that always appears as a flash. Sometimes it is cumulative. It adds dose to the body over time. It raises long-term health risks. It can damage electronics. It can force crews to hide in shelters during solar events. It can interrupt work outside. It can make surface operations more complicated. It can turn a planned day of repairs into a waiting period inside a protected compartment. Now, imagine a critical repair is needed outside the habitat. A pump is failing. A cable connection is unstable. A rover is stuck. A dust-covered system needs cleaning. Then, a solar radiation warning arrives. The crew may know exactly what needs to be fixed, but they may not be able to go outside safely. Waiting protects their bodies, but waiting may harm the system. Going outside may save the mission, but expose them to dangerous radiation. Mars does not always offer the choice between safe and unsafe. Sometimes it offers a choice between two different dangers. That is why being trapped on Mars is not just about a rocket refusing to launch. It is about living in a place where every repair, every delay, every weather event, and every biological problem can push the crew farther from the return plan. And Mars has one more enemy that sounds almost harmless: dust. Martian dust is not just dirt. It is fine, persistent, electrostatically troublesome, and able to coat surfaces everywhere. It can cover solar panels, enter joints, scratch seals, cling to suits, contaminate airlocks, reduce radiator performance, and become a constant maintenance burden. On the Moon, Apollo astronauts quickly learned that dust could be irritating and invasive. Mars dust would bring its own chemical and mechanical challenges, and a mission lasting many months would give it time to become more than a nuisance. Dust is terrifying because it is small. A giant rock is obvious. A canyon is obvious. A cliff is obvious. Dust hides in edges, filters, folds, bearings, and seals. It rides back into the habitat on suits. It gathers on lenses. It changes how machines shed heat. It can reduce visibility during storms. It can make simple surfaces behave unpredictably. A Mars base would be a constant battle against particles. Airlocks would need cleaning systems. Suits might stay outside or attach through suit ports to keep dust from entering living spaces. Filters would need replacement. Robotic cleaners might sweep panels. Engineers would design seals carefully. But every solution adds mechanisms, and every mechanism can fail. Dust does not have to destroy a mission in one day. It can age it. It can make everything slightly harder. A hatch takes longer to close. A wheel motor runs hotter. A hinge grinds. A camera becomes cloudy. A connector needs cleaning. A filter clogs sooner than expected. A suit joint wears faster. A solar panel produces less power. Each one is manageable. Together, over months, they become the slow erosion of confidence. When humans imagine being trapped, they often picture a door slamming shut. On Mars, the door may close by millimeters. A little less power, a little more wear, a little less water reserve, a little more radiation exposure, a little less crew energy, a little more uncertainty about the ascent vehicle. And because the crew cannot resupply easily, every loss matters. A spare part used today is not available tomorrow. A filter replaced early means the inventory changes. A rover damaged during one traverse may reduce later rescue options. A suit problem may reduce the number of people who can work outside. A consumed medical supply may not be replaced for years. This is why logistics may be the real prison. A Mars crew lives inside a number of inventories: oxygen, nitrogen or buffer gas, water, food, spare filters, spare pumps, spare seals, tools, batteries, medicine, computer parts, rover parts, cleaning supplies, radiation detectors, emergency patches, scientific equipment, propellant. The list is endless because life is complicated. On Earth, civilization hides this complexity. When something breaks, supply chains move quietly around us. Trucks arrive, factories produce, stores restock, specialists travel. The modern world is a web of replacement. Mars would be a world without that web. The first crew would carry a small artificial supply chain with them, and everything outside it would be red rock, dust, ice deposits, carbon dioxide, sunlight, and distance. This is where the dream of living off the land becomes necessary. If astronauts can extract water, make oxygen, produce fuel, grow food, repair parts, recycle materials, and use Martian resources, Mars becomes less of a trap. But every one of those abilities has to be proven at the correct scale. Finding water from orbit is not the same as drilling, extracting, purifying, storing, and using it reliably. Growing plants in controlled experiments is not the same as feeding a crew year after year. 3D printing a part is not the same as producing certified hardware that can survive pressure, vibration, temperature, and life-critical use. Mars resources are not gifts waiting in boxes. They are raw problems. Water may be locked as ice underground or mixed with soil. Reaching it may require drilling, heating, mining, processing, and contamination control. The best deposits may not be near the safest landing sites. The safest landing sites may not be near the best science. The best science may not be near the easiest return trajectory. Every landing site is a compromise. And on Mars, compromise can decide survival. If the first crew lands near accessible ice, the mission gains options. If the ice is harder to reach than expected, the mission loses confidence. If mining equipment fails, the crew may have to rely only on stored reserves. If water extraction works slowly, schedules change. If the water contains chemicals that require extra processing, energy demand rises. If a drill breaks, the spare part may not exist. A person can die of thirst on a planet that contains water. Not because the water is absent, but because it is inaccessible at the time and place where it is needed. That is a Mars kind of danger. It is not enough for something to exist. It has to be reachable, usable, reliable, and connected to the return plan. The same is true for food. Early Mars crews would bring stored food, but a permanent presence would eventually need production. Growing food sounds hopeful, almost comforting. Green plants under artificial lights inside a Martian greenhouse could become one of the most emotional images of human expansion. But farming on Mars is not a garden project. It requires pressure, temperature control, water, nutrients, lighting, pest control, microbial management, pollination strategies, waste recycling, and protection from contamination. Plants do not care that humans are making history. They need stable conditions. If the greenhouse loses power, crops can die. If water becomes limited, yields drop. If disease spreads through a closed growing system, food production may collapse. If nutrients are not balanced, plants suffer. If dust enters equipment filters and fans struggle. If the crew spends too much time maintaining crops, other work suffers. Food is also psychological. Fresh growth can lift morale. The smell of living plants could remind astronauts of Earth in a place where Earth is no longer physically present. But dependence on crops can create new anxiety. A failed harvest on Earth may be an economic problem. A failed harvest on Mars can become a survival calculation. The first humans may not depend fully on farming, but they will depend on food planning. They will count calories. They will manage reserves. They will track shelf life. They will know how much remains if departure is delayed. They will understand that every extra month on Mars must be paid for in supplies, recycling efficiency, and system endurance. A return delay is never just a calendar problem. It is a food problem, a water problem, a medical problem, a crew morale problem, a spare parts problem, a radiation exposure problem, a power problem. This is why the phrase "trapped forever" does not need to mean an immediate disaster. It may mean the mission crosses from planned duration into unplanned survival. The crew may still be capable, the habitat may still be working, Earth may still be talking to them, but the mission clock changes. Instead of working toward return, they begin working to remain alive until return becomes possible again. And if return never becomes possible, Mars becomes home by force. The first part of that forced home would not look like science fiction cities. It would look like conservation. Use less, repair more, travel shorter distances, stay inside longer, reduce risk, preserve suits, protect the rover, keep the return vehicle alive. Every choice would become smaller and heavier. At first, the crew might still believe the delay is temporary. Another launch window, another repair attempt, another diagnostic plan from Earth, another way to reroute a system. Humans are good at hope, especially trained crews. They would not give up easily. They would work the problem, again and again. But Mars would keep asking the same question. What can you do with only what you have? This question is brutal because it removes imagination from survival. On Earth, we imagine solutions because resources can move. On Mars, solutions are bounded by inventory, energy, time, and biology. The crew can be brilliant, but brilliance cannot replace a missing part in every situation. Improvisation can save lives, but only when the materials available can be turned into something useful. Courage can keep people moving, but courage does not refill tanks. The first humans on Mars may be trapped not because they are weak, but because they are alive in a place where life has to be negotiated every hour. And then there is the journey home itself. Even if the crew successfully lifts off from Mars, the story is not over. Leaving the surface is only the first step. The ascent vehicle has to reach Mars orbit. It has to rendezvous with another spacecraft or transfer system. The crew has to dock or move across safely. The return spacecraft has to perform the correct burn at the correct time. Then, it must carry the crew across interplanetary space for months. Mars can trap the crew before launch. Space can trap them after launch. The return vehicle may be waiting in orbit, but if its systems are unhealthy, the crew may escape Mars only to enter another emergency. If rendezvous fails, they may be stranded in Mars orbit. If the return burn fails, they may remain trapped around Mars or enter the wrong solar orbit. If life support has degraded during the long wait, the ride home may become impossible. If the crew leaves too late, trajectory options may be worse. This is why a Mars mission is not one escape. It is many escapes chained together. Escape Earth, escape deep space transit, escape landing, escape surface dependence, escape Mars gravity, escape Mars orbit, escape interplanetary distance, re-enter Earth safely. The public may focus on the first and last images, launch from Earth and landing back home. But the danger hides in the middle, where cameras may show calm routines while hundreds of invisible dependencies decide whether the crew can ever return. A one-way Mars mission could happen by design. Some people have proposed the idea that settlers might go knowing they will never come back. That is one kind of story. But the more haunting possibility is different. A mission designed to return might become one-way by failure. The crew may leave Earth expecting to come home. Their families may count down the mission phases. The return vehicle may be part of the plan. The speeches may promise a round trip. And still, Mars may slowly change the answer. Not through evil, not through intention. Through distance, dust, timing, machinery, chemistry, health, and the simple fact that humans are trying to live on a planet that never evolved for them. This is the central fear of the first Mars crew. They may not be trapped by Mars because Mars is impossible. They may be trapped because Mars is almost possible. Close enough to reach, interesting enough to justify the risk, resource-rich enough to tempt planners, stable enough to imagine habitats, familiar enough to look like a desert world rather than a completely alien nightmare, but still hostile enough that one missing resource, one failed engine, one damaged system, or one closed launch window could turn the greatest expedition in history into the most isolated survival story ever lived. That is why Mars is so dangerous in the human imagination. It does not look utterly unreachable. It looks reachable just enough to invite us in. And once humans are standing there, the hardest part may not be proving that we can arrive. It may be proving that arrival was not a trap. The first trap is distance. The second trap is timing. The third trap is the return rocket. But the fourth trap is more subtle than all of them. It is the way Mars forces every system to age in a place where replacement is almost impossible. A new habitat on landing day is one thing. A habitat after 500 sols is another. Fans have been spinning. Filters have been collecting particles. Pumps have been cycling. Seals have been compressed and relaxed through temperature changes. Computers have been running. Batteries have been charging and discharging. Airlocks have opened and closed. Rovers have crossed rough ground. Suits have bent at the joints again and again. Nothing stays new. On Earth, aging equipment enters a maintenance ecosystem. Parts are ordered. Technicians rotate. Tools improve. Facilities are upgraded. If a machine is too worn, a new one is shipped in. If a building needs repair, crews arrive with materials. On Mars, aging is personal. The crew watches the mission grow older with them. A fan that sounds slightly different may matter. A rover wheel drawing more current may matter. A suit joint feeling rough may matter. A habitat panel that develops a small thermal issue may matter. Each change is a message from the future. It says that the base is not frozen in the perfect state it had on the day the plan was written. It is being used. And anything that is used can break. The scariest failures may be the boring ones. Not explosions, not cinematic cracks in the wall, just ordinary mechanical decline in an extraordinary place. A bearing worn down by dust. A chemical cartridge saturated earlier than expected. A sensor drifting out of calibration. A cable damaged during an EVA. A latch that requires more force than before. A battery pack that no longer holds the same charge. This becomes especially serious because early crews may need to work outside often. Exploration, setup, repair, sample collection, cable laying, equipment cleaning, rover maintenance, surface inspections, construction, and science all require EVA time or robotics. The more people go outside, the more suits and airlocks are used. The less they go outside, the less they can fix, build, and explore. A Mars base must balance exposure against progress. Too much caution, and systems may not be maintained fast enough. Too much activity, and critical equipment wears down faster. Even success has a cost. If the crew discovers an amazing site 10 kilometers away, reaching it may use rover life, suit time, batteries, crew energy, and risk. If they ignore it, the mission loses science value. If they go, they add stress to systems that also support survival. The first Mars mission will be filled with choices where every option consumes something. And the most expensive decision is the one that leads away from the return plan. At some point, the crew may need to ask whether a repair, a traverse, a sample mission, or a construction task is worth the risk to the systems that bring them home. Science wants more. Exploration wants more. History wants more. But survival may keep asking for less. Less travel, less exposure, less strain, less uncertainty. That is one of the strangest forms of being trapped. You are on a whole world, but you can only safely occupy a tiny part of it. The horizon may be open, but the reachable world is defined by rover range, oxygen, battery levels, terrain, time, communication, and the ability to get back before something changes. The first humans on Mars may stand on a planet and still live like people inside a locked room. Their room just happens to have a red desert around it. That desert would be beautiful. It would also be deceptive. Mars landscapes can look like places on Earth. Dry valleys, rocks, cliffs, dunes, plains, ancient riverbeds. This visual familiarity may be dangerous because it makes the planet feel almost understandable. A person sees a hill and thinks of hiking. They see sand and think of deserts. They see a horizon and think of travel. But Mars is not a desert in the Earth sense. An Earth desert still has breathable air. It has pressure. It has weather inside a living planet. It has rescue possibilities. It has microbes, wind shaped by a thick atmosphere, and a sky under the same protection that lets human blood remain liquid without a suit. Mars only looks like a desert. In practice, it is a vacuum-adjacent, radiation-exposed, freezing, dry, dusty, low-gravity world where the human body survives only inside equipment. Mars will have details. Dust may behave differently around full-scale human equipment than expected. Habitats may need maintenance patterns that were not obvious in tests. Crew psychology may react to the planet in unexpected ways. Local terrain may create navigation problems. Resource extraction may be slower. Medical issues may appear. Radiation events may interrupt schedules. Software may fail in combinations no simulation fully predicted. The first crew will not be exploring the Mars of diagrams. They will be exploring the Mars that actually happens. And actual Mars does not have to match the plan. This is why pre-deployment helps but cannot remove the danger. Sending cargo first is smart. Testing systems before crew departure is smart. Producing return propellant before landing is smart. But pre-deployed systems are also exposed systems. They must survive waiting. They must remain healthy without humans nearby. They must communicate their condition accurately. They must not be buried, coated, damaged, or degraded beyond use. A return rocket sitting on Mars is not automatically a guarantee. It is an object aging on another planet. It has tanks, lines, electronics, sensors, engines, seals, and structure. It may need to remain ready across temperature cycles, dust exposure, and long periods of dormancy. If propellant is stored, it must be kept stable. If it is produced locally, production and storage must be verified. If the vehicle is checked remotely, the data must be trusted. If something looks wrong, someone has to decide whether it is truly wrong or only a sensor issue. Imagine the crew is months into the surface mission. The departure window is approaching. The ascent vehicle reports a pressure reading outside the expected range. It might be a sensor, it might be a leak, it might be a temperature effect, it might be a sign of a serious problem. Earth receives the data minutes later. Engineers debate. Commands are sent back. Tests are run. The crew inspects what they can. Every action takes time. Every day moves the planets. Every conclusion carries risk. If they launch, and the reading was a real warning, they may die. If they delay, and the reading was harmless, they may miss the window. If they attempt repair and damage the system, they may lose the vehicle. If they do nothing, they may run out of options. That is Mars as a trap, not a single locked door, but a decision tree where every branch is dangerous. The first humans on Mars would live inside that kind of decision tree every day. Even communication with Earth would change the feeling of help. People often imagine mission control as a constant voice in the astronaut's ears, like Apollo. But Mars is too far for real-time conversation. Depending on the distance between the planets, signals can take several minutes or much longer to travel one way. A question and answer can take tens of minutes. During critical operations, that delay matters. Mission control can advise. It cannot react instantly. If an alarm sounds, the crew acts. If a rover slips, the crew acts. If a suit warning appears, the crew acts. If an engine test behaves strangely, the crew acts. Earth becomes less like a controller and more like a distant council. That distance can feel lonely, but it also means responsibility cannot be outsourced. The crew has to understand the systems deeply enough to respond without waiting. They need autonomy, not as a luxury, but as survival. Even if everything works, the human body will be changing. Mars gravity is about 38% of Earth's gravity. That is more than the Moon, but far less than what our bodies evolved for. Long-duration exposure to reduced gravity may affect muscles, bones, cardiovascular function, balance, coordination, and the way the body handles fluids. Exercise can help, but it is not magic. The crew would arrive after months in microgravity or artificial mitigation. Then, adapt to Mars gravity, then later need to withstand launch, transfer, and Earth's gravity again. Returning from Mars is not only a rocket problem, it is a body problem. Can the crew climb ladders after months on Mars? Can they respond to emergencies during launch? Can they perform docking tasks? Can they survive acceleration after illness, injury, or bone loss? Can they function during the return cruise? When they reach Earth, can they tolerate re-entry and landing? A mission plan may assume healthy astronauts. Mars may create tired astronauts, injured astronauts, stressed astronauts, partially deconditioned astronauts, and people who have spent months living under environmental pressure. Human endurance is a system too, and it has limits. If one person becomes unable to participate, the workload shifts to the others. If two people are injured, repair capability falls. If the doctor becomes sick, medical risk rises. If the engineer most familiar with the ascent vehicle is hurt, return confidence drops. Crew selection can reduce risk, but it cannot make people unbreakable. The biggest public fear may be that a Mars rocket cannot launch. The deeper fear is that by the time it can launch, the mission may no longer be the same mission. Maybe supplies are lower. Maybe one astronaut is injured. Maybe the rover is damaged. Maybe propellant production was delayed. Maybe a dust storm consumed power margin. Maybe radiation exposure changed medical recommendations. Maybe the return spacecraft in orbit has developed a problem. Maybe Earth is asking them to wait. Maybe waiting is more dangerous than leaving. At that point, the crew is not simply following a plan. They are choosing between imperfect futures. This is the point where Mars stops being a place in the sky and becomes a pressure chamber for human decision-making. Every exploration frontier has risk, but Mars combines too many categories at once. It is physically hostile, mechanically demanding, logistically distant, psychologically isolating, medically limited, and governed by orbital timing. Most dangerous places on Earth have one or two of those features. Mars has all of them, and then adds the fact that the entire mission is happening on another planet. This does not mean humans should never go. It means the romantic version is incomplete. A Mars landing would be glorious, but glory is only the opening scene. The real story begins after the dust settles, when the crew has to make the planet behave like a temporary home and make the return system remain trustworthy. That work is slower, quieter, and more dangerous than the first step. The first humans on Mars may be trapped forever because Mars will not have to beat them in one obvious way. It only has to outlast the weak parts of the plan. A plan is written in clean rooms, offices, simulations, reviews, and mission diagrams. Mars answers with temperature, dust, radiation, wear, delay, and terrain. The plan assumes enough margin. Mars tests whether enough was truly enough. If the margin holds, the crew comes home. If the margin breaks, the crew waits. And if waiting breaks more margins, the mission enters the most terrifying territory of all. A place where survival continues, but return becomes uncertain. That is where this first half of the journey leaves us. Not with a failed mission, not with disaster, but with the uncomfortable understanding that a successful landing on Mars is not the same thing as a successful Mars mission. The astronauts have arrived. They are alive. The habitat is standing. The cameras are working. The world is watching. But the planet beneath them is still asking the only question that truly matters. Can you leave? The answer begins with the hardest machine on the mission, the one that has to lift them off Mars. Not the lander that brought them down. Not the habitat that keeps them breathing. Not the rover that carries them across the red ground. The most important machine may be the one waiting quietly nearby, wrapped in dust covers, heaters, sensors, valves, tanks, batteries, insulation, and months of silent anxiety. It is the ascent vehicle. On Earth, a rocket launch is a national event. There are towers, roads, control rooms, fuel farms, emergency crews, weather teams, tracking stations, recovery ships, replacement parts, and thousands of people watching every number before the countdown is allowed to continue. If something looks wrong, the launch can be scrubbed. A valve can be replaced. A technician can climb a service tower. Another attempt can happen later. On Mars, there is no tower. There is no launch pad crew. There is no rescue helicopter. There is no local factory. There is only the rocket, the astronauts, the red dirt underneath it, and Earth speaking through a delay. That changes everything. A Mars ascent vehicle does not only have to work, it has to work after a long journey through space, after landing shock, after months or years of cold nights and warm days, after dust has tried to enter every seam, after radiation has aged electronics, after seals have sat under pressure, after batteries have cycled, after propellant lines have been heated and cooled, and after the crew has already spent a dangerous portion of their mission simply staying alive. A machine can pass every test on Earth and still meet something on Mars that was not fully copied in a laboratory. The dust is different. The cold is different. The repair environment is different. The consequences are different. If the rocket does not launch from Earth, a mission is delayed. If the rocket does not launch from Mars, people may remain there until another planet-sized opportunity comes around. And that opportunity is not controlled by courage. It is controlled by orbital mechanics. Earth and Mars do not sit beside each other like two islands with a regular ferry. They move around the sun at different speeds, sometimes relatively close, sometimes on opposite sides of the inner solar system. A useful transfer window opens roughly every 26 months. That means a stranded crew may not be waiting days for a rescue plan. They may be waiting through seasons, equipment wear, supply limits, crew fatigue, and the knowledge that even after Earth launches help, the help must still travel across interplanetary space. This is why the phrase "trapped forever" does not always mean instant disaster. It may mean something slower. A crew can be alive and still trapped. A habitat can have oxygen and still be a prison. A return rocket can exist and still not be trusted. A rescue mission can be planned and still arrive too late for the specific problem that began the crisis. Imagine the first Mars crew standing near the ascent vehicle before the scheduled departure. The dust has been cleared as well as possible. The tanks show pressure. The guidance system is awake. Earth has checked the telemetry. Everyone knows this moment has been simulated for years. But the astronauts also know something the simulation could never make emotional. They are not launching from a spaceport. They are launching from the surface of another planet. If the rocket rises, they must reach the right path, at the right time, with the right velocity, to meet the waiting spacecraft in Mars orbit. If the burn is wrong, there may be no second try. If the rocket underperforms, they may end up in an orbit too low, too elliptical, or too far from the return craft. If docking fails, they may have only limited supplies inside the ascent vehicle. If the orbiting craft has a fault, Mars has taken them halfway home and then stopped them above the world they were trying to leave. This is not like missing a train. This is missing a moving target in the sky while your home planet is tens or hundreds of millions of kilometers away. The terrifying part is that return is not a single step. It is a chain. Launch from Mars, reach orbit, find the return vehicle, rendezvous, dock, transfer crew, check life support, perform the departure burn, survive months of cruise, protect against radiation, maintain the spacecraft, aim for Earth, enter the atmosphere, land, or splash down alive. Every link has to hold. If one link fails, the crew may still be alive, but their path home can vanish. This is the trap that hides inside successful exploration. The mission does not fail only when something explodes. It can fail when a component refuses to respond, when a docking seal will not confirm, when a computer reboots at the wrong time, when a leak rate is slightly higher than predicted, when fuel margin becomes too thin, or when an astronaut looks at the checklist and realizes the next safe option is no longer on the page. Mars does not need to be dramatic to be deadly. It only needs to be unforgiving. And that unforgiving nature begins long before the crew climbs into the ascent vehicle, because the ascent vehicle itself depends on what happened during the surface stay. If the mission brought all return propellant from Earth, the launch mass would be enormous. Every kilogram landed on Mars requires fuel, shielding, structure, testing, and years of mission design. The more mass you bring, the harder the landing becomes. The harder the landing becomes, the more complex the system grows. And the more complex the system grows, the more places exist for failure to hide. That is why many Mars return concepts look toward using local resources. Mars has a thin atmosphere mostly made of carbon dioxide. If a system can take that carbon dioxide and process it, oxygen may be produced for breathing, or rocket oxidizer. NASA's MOXIE experiment on Perseverance demonstrated that oxygen can be extracted from Martian CO2. But a human return mission would need the idea at a much larger scale, over a longer time, with reliability high enough that lives depend on it. A demonstration is a beginning. A survival system is another world. For a crew, the question is not only whether oxygen can be made on Mars, it is whether enough can be made, stored, kept clean, kept cold or pressurized if needed, monitored, protected, and delivered into a rocket system at the exact time the mission needs it. A machine that makes oxygen in a rover is inspiring. A machine that makes return propellant for human beings must behave like a lifeline. If the production rate is lower than expected, the schedule slips. If dust reduces power, production slows. If a compressor wears out, the repair must be possible with tools on hand. If a filter clogs, there must be replacements. If a tank sensor disagrees with another sensor, the crew must decide whether the problem is measurement or reality. If the propellant reaches quantity but not quality, the rocket may technically be full and still unsafe. This is where being trapped can begin without anyone noticing at first. The mission clock says there are months left. The propellant plant is running. The habitat is stable. The crew is tired but functional. Then the numbers drift. Not enough to cause panic, just enough to require a meeting. A little less output per day. A little more maintenance time. A warning light that appears twice in 1 week. A heater drawing more power than expected. A storage tank that needs additional checks. At first, these are engineering problems. Then they become schedule problems. Then they become mission risk. Then, slowly, they become the question everyone fears. Will the rocket be ready before the window closes? A return window is not patient. It does not wait for repairs. It does not care that a pump failed late in the mission. If the launch cannot happen at the right time, the crew may be forced to stay until the next alignment. That could mean another long stretch of life support, another Martian winter or summer, more radiation exposure, more wear on suits, more use of spare parts, more psychological pressure, and a rescue architecture that becomes harder because the original mission has already consumed resources. A delay of 1 month on Earth can be frustrating. A delay of 1 month on Mars can be the doorway to another 2 years. And during those 2 years, Mars keeps charging interest. Food stores decline. Filters age. Seals crack. Motors accumulate dust. Solar panels lose efficiency unless cleaned. Nuclear systems, if present, continue to produce power, but still require thermal management and monitoring. Water recycling systems collect deposits, microbes, and mechanical wear. Crew health changes. morale changes. The habitat becomes familiar, then small, then possibly unbearable. The first emergency may be solved, the second may be manageable. The third may be the one that arrives after the spares are gone. That is why a real Mars mission cannot treat return as something that happens at the end. Return has to be alive from the beginning. Before the crew ever leaves Earth, the system that brings them back must already be protected by redundancy, testing, backup plans, and enough humility to admit that Mars will not behave like a friendly laboratory. But even if the ascent vehicle is perfect, another problem waits above it: Mars orbit. A crew that launches from the surface is not home. They are only between traps. To come back to Earth, they likely need to meet an orbiting spacecraft or use a larger return vehicle already placed around Mars. That means navigation has to be precise. The ascent stage must reach a usable orbit. The return craft must be healthy. The two vehicles must find each other, approach each other, match speed, dock, seal, pressurize, and allow the crew to transfer safely. Docking in Earth orbit is difficult, but it has history, infrastructure, experience, tracking networks, and relatively nearby support. Docking around Mars after months on the surface is different. The crew may be physically weaker. The vehicles may have been waiting longer. The communication delay means Earth can advise, but not joystick the moment. The crew and onboard computers must carry the operation. A docking port that will not align is not a small annoyance. A stuck hatch is not a simple hardware issue. A guidance error is not just a software bug. It is the difference between a spacecraft being a homeward path and becoming another object in the Martian sky. Now imagine the astronauts inside the small ascent cabin. Mars is below them, huge and rust-colored. No longer a landscape beneath their boots, but a curved world turning under their window. The return spacecraft is somewhere ahead. They can see numbers, indicators, relative velocity, distance, fuel, pressure, suit status, oxygen reserve. They have left the surface, but they have not escaped. This middle zone may be one of the loneliest stages of the entire mission. On the surface, they at least have a habitat, supplies, rovers, tools, and ground. In orbit, inside a small vehicle with limited consumables, time becomes sharper. A delay of hours matters. A maneuver error matters. A docking delay matters. Mars orbit offers no safe harbor. There is no station waiting with food, no repair dock, no emergency crew, no second ascent vehicle within walking distance. Only the equipment that was sent there years earlier and the fragile choreography required to use it. If the return vehicle is healthy, the crew transfers and prepares for the burn home. If it is not healthy, choice is narrow. Can they repair it? Can they wait inside it? Can they return to the surface? Usually, returning to the surface after ascent may not be practical. The lander that brought them down is not a reusable shuttle. The ascent vehicle is designed to climb, not to become a Mars taxi. So a crew could leave Mars and still be trapped by Mars, not on the ground, above it. This is the deeper meaning of a one-way risk. A Mars mission is not one bridge. It is several bridges in a row, and some burn behind you after you cross them. Landing burns the bridge of easy return. Surface stay consumes the bridge of fresh equipment. Ascent burns the bridge of the habitat. Rendezvous burns the bridge of the ascent vehicle. Earth departure burns the bridge of Mars orbit. Each step commits the crew to the next system. If the next system fails, the previous one may no longer be reachable. This is why engineers obsess over margins. To the public, margin can sound like extra. Extra fuel, extra power, extra food, extra time, extra oxygen, extra parts. But in deep space, margin is not luxury. It is the space between a problem and a catastrophe. The first humans on Mars may be trapped forever if the mission carries enough to succeed only in the version where everything behaves. Mars will not promise that version. It will offer dust, cold, uncertainty, and the ordinary decay of machines. It will offer human bodies that do not stay perfect. It will offer communication delays at the exact moments when people want immediate certainty. It will offer a sky where Earth is a star and home is a calculation. After rendezvous, after transfer, after the return burn, the crew may finally be heading back. This sounds like the safe part, but interplanetary return is not a hallway. It is months of exposure inside a machine that cannot stop at a hospital, cannot pull into a repair bay, and cannot turn around easily if the trajectory has committed them. The return cruise is the last long test. The crew has already endured launch from Earth, months in space, landing on Mars, surface operations, lower gravity, radiation, stress, dust, limited sleep, repairs, ascent, docking, and departure. They now have to survive the journey home with bodies and equipment that have already been used hard. This is where fatigue can become dangerous. A fresh crew reacts one way. A crew, after years of mission pressure, reacts another. Checklists are still followed, but concentration is a resource. Patience is a resource. Trust is a resource. A small disagreement about a procedure can carry the weight of everything that happened before. The spacecraft becomes quieter than the surface habitat, but not necessarily easier. Outside, there is no ground. Inside, every smell, sound, vibration, and warning tone matters. A pump that sounds different can ruin sleep. A sensor spike can start hours of analysis. A radiation alert can force people into a sheltered area. A medical symptom can become a debate between waiting, treating, conserving supplies, and using equipment that might be needed later. The crew may be technically on the way home and still not feel free, because Mars is behind them, but Earth is not yet close. This is one of the cruelest parts of interplanetary travel. The emotional story says, the astronauts leave Mars and come home. The physical story says they enter another dangerous environment with no quick exit. The distance that once separated them from Mars now separates them from Earth. For months they live between worlds. If the spacecraft loses a critical system, there is no backup ship minutes away. If life support begins to fail, Earth can send procedures, but not parts. If a solar particle event occurs, shielding becomes the difference between exposure and survival. If an engine correction is missed or underperforms, the arrival path may need to be recovered with limited fuel. Even the return to Earth is not simple. The spacecraft must hit the atmosphere correctly. Too shallow, and it may skip away or fail to slow as planned. Too steep, and heating and forces rise. The crew returning from Mars may be weaker than when they left. They may have spent years away from Earth gravity. They may face re-entry forces after long deconditioning. Their bodies must endure the final violent minutes after surviving a mission measured in years. A Mars mission can be lost near the beginning. It can be lost in the middle. It can be lost after success seems close. That is what makes the trapped forever idea so disturbing. It is not one scenario. It is a family of scenarios. Some happen on the surface, some happen in orbit. Some happen during the trip home. Some happen before the crew even launches from Earth. If a mission design quietly accepts too much risk because the dream feels too important to delay. And there is another version, perhaps the strangest one. The crew may not be trapped by failure. They may be trapped by success that becomes permanent. At first, a Mars outpost might be presented as temporary. The first crew lands, works, tests systems, produces fuel, explores, learns, and returns. Later crews improve the base. More habitats arrive. More power units unfold. More cargo lands. Greenhouses expand. Landing pads become more permanent. Rovers travel farther, the outpost becomes a place with a name. Then, the language changes. Mission becomes settlement. Settlement becomes colony. Colony becomes home. And once that happens, the question is no longer only whether people can return from Mars. It becomes whether some people will be expected not to. This is not automatically evil. Every permanent human community began because someone stayed somewhere. But Mars is not an island, a valley, or a continent. Mars is a planet where every breath depends on technology. Choosing to live there permanently is different from choosing a difficult life on Earth. On Earth, even harsh environments belong to a biosphere. Antarctica is brutal, but it has Earth air above it, Earth gravity below it, Earth oceans around it, and rescue systems that can sometimes reach it. Deserts can kill, but the planet still supports life in countless connected ways. Mars has no such background mercy. A permanent Mars resident would live inside machines forever. Not for a season, not for a mission. Forever, unless they leave. And leaving may become harder the longer they stay. Muscles adapt to lower gravity. Bones lose loading. The cardiovascular system changes. Skills specialize around local survival. The outpost demands maintenance. Responsibilities grow. Children, if they ever exist there, would raise questions no exploration plan can treat as a simple extension of astronaut training. Could a child born on Mars safely develop? Could they return to Earth gravity? Would their bones, heart, balance, immune system, and development handle the difference? Would they even feel Earth as home, or as a heavy world their bodies were not built for? These questions push the Mars trap from engineering into ethics. A trained adult can accept risk. A future child cannot consent to being born in a world where stepping outside requires a pressure suit and returning to the species' home planet may be physically dangerous. That does not mean Mars settlement is impossible. It means the word colony carries more weight than it appears to. A colony is not just hardware. It is law, medicine, reproduction, education, grief, mental health, identity, and the right to leave. A true home is not only a place where people can survive, it is a place people are not forced to remain because survival made departure impossible. This is where the title becomes most uncomfortable. The first humans on Mars may be trapped forever, not only because a rocket breaks, but because a human presence can become too complex to reverse. Once infrastructure exists, once money is invested, once symbols are built, once people are born or buried there, Mars becomes more than a mission objective. It becomes a commitment, and commitments can become cages when the exit is too expensive, too dangerous, or too politically painful to admit. Imagine a crew member whose health declines after 2 surface cycles. They want to go home. Earth doctors agree that return is best, but the next launch window is months away. The ascent vehicle has limited capacity. Another crew member is more critical to rotate out. The base cannot spare both engineers. The return craft has mass limits. The medical system can support them on Mars for now. A decision is delayed. No one calls it abandonment. No one intends cruelty. But the planet has changed the meaning of choice. On Earth, a person can usually leave a job, a city, or a country with enough planning. On Mars, leaving is a launch campaign. It consumes propellant, orbital timing, vehicle capacity, medical assessment, risk approval, and political will. Freedom of movement becomes a rocket equation. That may be one of the most alien parts of living there. Not the red sky, not the dust, not the cold. The fact that the simple human sentence "I want to go home" would require a mission architecture. This is why serious Mars planning must ask uncomfortable questions before the first footprints are made. How many return seats exist? Who gets priority if capacity is limited? What happens if someone refuses to stay? What happens if someone refuses to leave? Who commands a settlement when Earth is minutes away by radio, but months away by physics? Can Earth legally order people on Mars to take a risk? Can a crew overrule Earth because they understand local conditions better? At what point does a base stop being an expedition and become a society? These questions sound political, but on Mars, politics becomes life support. Governance is not abstract when one decision controls oxygen, power, medical supplies, rover usage, or launch readiness. A conflict that would be annoying on Earth can become dangerous in a sealed habitat. A settlement needs rules before the crisis, not during it. It needs trusted authority. It needs transparent priorities. It needs mental health systems that are not treated as optional. It needs conflict resolution for people who cannot walk away. Because when the door opens to the outside, there is no outside world waiting in the normal human sense. There is only Mars. And Mars does not care who is right. The physical environment will punish the entire group if the social environment fails. That is another way a crew can become trapped. Not by broken rockets, but by broken cooperation. A Mars base depends on shared routines. Airlocks must be used correctly. Contamination must be controlled. Tools must be returned. Power budgets must be respected. Medical symptoms must be reported. Schedules must be followed, but also adapted. People must trust that the person on the next shift did the invisible task properly. Trust becomes infrastructure. If trust breaks, every task becomes heavier. If every task becomes heavier, fatigue grows. If fatigue grows, mistakes increase. If mistakes increase, the environment gets more chances. This is not drama added to science. It is part of the system. Human beings are not passengers inside the technology. They are components of the mission. And components can be overloaded. Mars will test not just equipment, but relationships. It will test leadership. It will test patience. It will test whether people can remain kind when they are frightened, bored, tired, confined, watched by Earth, and surrounded by a planet that will kill them without hesitation. And because communication is delayed, many decisions must happen locally. Earth can send advice, but advice arrives after the moment has already begun. During a fire, leak, rover accident, suit puncture, or medical collapse, the crew cannot wait for a perfect answer from home. They have to become their own emergency services, their own hospital, their own repair crew, their own government, their own witnesses. This autonomy sounds heroic until it becomes lonely. A person making a life or death decision on Mars may know that experts on Earth will later analyze every choice, but cannot help in real time. They may know millions of people are emotionally present, but physically absent. They may hear a calm voice from mission control minutes after the hardest part is over. That delay can make Earth feel less like a parent and more like a memory. Over time, this could change the crew's psychology. At first, Earth is the center. Every message matters. Every family video is watched. Every sunrise on Earth mentioned by loved ones is painful and beautiful. But after months and years, Mars routines take over. The crew knows the sound of the habitat at night. They know which pump vibrates. They know the smell of dust near the suit lock. They know the color of the horizon before a storm. They know where the rover wheels slip. Mars becomes familiar. Familiar does not mean safe. A prison can become familiar. A dangerous home can become familiar. A place you cannot easily leave can become part of you. This is the emotional trap. The crew may fear being stuck and also fear leaving. They may miss Earth and also wonder whether Earth will feel too loud, too heavy, too uncontrolled, too full of weather, oceans, crowds, and open air. After living in a world where every system is monitored, Earth may feel overwhelming in a way no one expected. The return may not simply restore them. It may break them differently. That is why the Mars problem is not only how to survive there, but how to remain human there. Not in a poetic sense, in a practical sense. Humans need privacy, purpose, touch, choice, variety, sunlight, sleep, conflict, forgiveness, and a future that feels larger than maintenance. A base that only keeps people alive is not enough. A crew can have calories and still lose hope. They can have oxygen and still feel buried. They can have work and still feel trapped inside an endless emergency. If the first Mars mission becomes longer than planned, mental health may become as important as oxygen production. The crew will need meaningful goals beyond waiting. They will need exploration routes, science tasks, construction projects, communication rituals, exercise, entertainment, and honest contact with Earth. They will need to feel that each day is not only another day survived, but another day with direction. Without that, Mars can shrink. A whole planet can become a few rooms. A horizon can become decoration behind a window. The dream can become inventory management. This is where many popular Mars visions become too clean. They show domes, farms, astronauts walking under red skies, and rockets rising dramatically from dust. They rarely show the 10th month of fixing the same valve type. They rarely show the smell of recycled air after a stressful week. They rarely show an argument about whether to use spare power on a science rover or a water extractor. They rarely show the crew member who stopped sleeping because the return propellant numbers are behind schedule. Real exploration is made of details. The trap is hidden in details too. A missing gasket, a cracked visor, a failed crop, a medicine that expires, a rover battery that degrades, a sample container that contaminates a clean area, a software patch that creates a new error, a storm that lasts longer than expected, a soup joint that collects dust and begins to resist motion, a crew member who hides pain because they do not want to be removed from a critical task. None of these alone has to end the mission. Together, they can bend it. That bending is what Mars does. It may not snap the plan at once. It slowly pushes every part of the mission away from the ideal version. The question becomes how much bending the design can absorb before return is no longer a confident path. This is why rescue is such a difficult word. On Earth, rescue often means speed. Ambulance, helicopter, ship, fire crew, evacuation aircraft. On Mars, rescue may mean designing, building, launching, transferring, landing, docking, or supplying across millions of kilometers. Even if a rescue vehicle is ready on Earth, Earth still has to wait for launch energy, trajectory, travel time, landing conditions, and the condition of the crew when help arrives. A Mars rescue cannot be improvised like a movie scene. There is no secret rocket that simply leaves tomorrow and reaches them next week. The solar system has geometry. Geometry has no sympathy. If a crew is stranded because they missed a return window, help may not reach them until the next chain of windows and transfers allows it. During that time, the stranded crew must still operate. They must preserve food, repair systems, maintain power, manage waste, keep water clean, and protect themselves from radiation and dust. A rescue mission that arrives after the habitat fails is not rescue. A rescue mission that arrives after crew health collapses is not rescue. A rescue mission that needs the stranded crew to perform complex landing site preparation may fail if the crew is no longer capable. So rescue must be designed before the mission, not imagined afterward. This could mean pre-positioned supplies, backup ascent capability, multiple power sources, spare habitats, redundant communication relays, extra rovers, robotic repair assistants, emergency shelters along travel routes, orbiting assets that can support different scenarios. It may even mean sending return equipment years ahead and refusing to launch humans until the return system has already proven itself on Mars. That last idea may be the most important. Do not send people to Mars and then hope the return system works. Send the return system first. Make it produce propellant. Make it survive dust and cold. Make it report full tanks. Make it prove that the path home exists before human footprints arrive. This is less romantic, but far more honest. A human Mars mission should not be a gamble that becomes heroic only if the crew accepts being trapped. It should be designed so that coming home is not an afterthought. The safest first Mars crew may be the one that lands beside a return vehicle already waiting like a promise that has been tested by the planet itself. Even then, nothing is guaranteed. But the nature of the risk changes. The crew is no longer betting on an unproven factory after arrival. They are using a system that has already endured Mars. That does not remove danger, but it removes one of the cruelest uncertainties. The same principle applies to habitats. A base should not be a single shell with no backup. If one module fails, there must be somewhere to go. If one airlock jams, there must be another path. If one power line fails, another route must exist. If one water processor stops, storage and backup processing must buy time. The base should be designed like a small organism with multiple ways to keep blood flowing. But redundancy costs mass. Mass costs launches. Launches cost money. Money creates pressure to simplify. And simplification creates risk. That is the endless argument inside Mars planning. The safest mission is heavy, slow, expensive, and filled with backups. The exciting mission is lean, bold, and faster to announce. History often celebrates boldness, but Mars may reward patience. A rushed mission may reach the surface first. A patient mission is more likely to bring people back. This is where public storytelling matters. If the world demands a Mars landing as a spectacle, agencies and companies may feel pressure to deliver the dramatic scene, the first boot, the flag, the speech, the camera shot, the human silhouette under a salmon sky. But the real measure should not be the landing. It should be the return. A mission that lands humans on Mars and cannot bring them home is not automatically a triumph. It may be remembered as courage, but also as a failure to respect the full problem. The first footprint is only half a sentence. The final word is written when the crew is safely back, or when a permanent settlement has enough capability that staying is truly a choice. Anything between those two states is the danger zone. Temporary mission without reliable return. Permanent settlement without mature independence. That is where people can become trapped by ambition. There is another problem that makes independence harder. Mars is not rich in the way science fiction sometimes suggests. It has resources, yes. Carbon dioxide atmosphere, water ice in some places, minerals, regolith, sunlight, though weaker than on Earth, deuterium, and other scientific interests. But a resource is not useful simply because it exists. It must be found, reached, extracted, processed, purified, stored, and turned into something the base can use. Water ice buried under regolith is not a glass of water. Carbon dioxide in the air is not a full oxygen tank. Dusty soil is not fertile farmland. Iron oxide in the ground is not a steel beam. Every local resource requires an industrial chain. And an industrial chain requires equipment, power, maintenance, sensors, spare parts, and people who know how to fix the machines that fix the machines. That last phrase may define the difference between outpost and civilization. A small crew can operate equipment. A settlement must repair and eventually manufacture the equipment. If a pump breaks and the replacement came from Earth, the base is dependent. If the replacement can be made locally, the base is less dependent. If the tools that make the replacement need parts from Earth, dependency remains only one layer deeper. True independence is not having a greenhouse and a rover. It is having enough industrial depth that a failure does not immediately become a request to another planet. This is extremely hard. Modern life on Earth rests on global supply chains so complex that no single city can reproduce them alone. Electronics, medicines, seals, bearings, chips, optics, lubricants, medical devices, pressure vessels, motors, solar cells, nuclear components, fertilizers, sterilized packaging, sensors, batteries, and software tools all come from networks of industries. A Mars settlement would begin with almost none of that. It would be like trying to build a modern hospital, farm, power plant, airport, machine shop, water plant, and rocket base inside Antarctica, except Antarctica would be in a vacuum-like atmosphere, under higher radiation, with delayed communication and no surrounding biosphere. This does not make Mars settlement impossible forever. It makes the first generations fragile. They would live inside a technological bubble supplied by Earth. As long as cargo arrives, the bubble grows. If cargo slows, the bubble learns how dependent it really is. A political crisis on Earth could matter on Mars. A launch failure could matter. A funding cut could matter. A supply chain disruption could matter. A war, economic collapse, or shift in public attention could turn a proud settlement into a distant obligation. The people on Mars would not control all the systems that keep them alive. Some of those systems would still be factories, budgets, launch pads, and decisions on Earth. That is a different kind of trap. You can be trapped on Mars by Mars itself. You can also be trapped there by Earth, losing interest. This possibility is rarely placed at the center of the dream, but it should be. A settlement is not safe because the first ships arrive. It is safe when the flow of supplies can survive politics, economics, accidents, and time. If people are living permanently on another planet, supporting them cannot depend on excitement alone. Excitement fades. Infrastructure must remain. The first Mars residents would need a civilization-level promise from the planet they left behind, or enough local capability to survive if that promise weakens. Neither is easy. A 2-year mission is hard. A 20-year settlement is another category. A 100-year human presence is not exploration anymore. It is history being built in a place that constantly tries to erase the human body. The early years would probably be the most vulnerable. Too many systems would be new. Too many procedures would be untested in real life. Too few people would be available for too many specialties. A small crew might include engineers, doctors, geologists, pilots, biologists, and technicians, but no crew can contain every possible expert. Earth can advise, but hands must be local. If the only person trained deeply on one system becomes sick, the base loses capability. If 2 people conflict badly, the base loses stability. If one person dies, the emotional and operational shock affects everyone. Death on Mars is not only personal tragedy. It is a logistics, medical, psychological, cultural, and planetary protection problem. What happens to a body? Can it be returned to Earth? Should it be buried on Mars? Can burial contaminate scientific sites? How does a small crew grieve when work cannot stop? What ritual is possible in a place where even opening a door is a procedure? These questions sound dark, but avoiding them would be childish. A mission serious enough to send humans to Mars must be serious enough to imagine loss. Not because loss is certain, but because pretending otherwise makes every plan weaker. A crew that is trapped may have to face grief, without evacuation, without family physically present, without a normal funeral, and without the psychological release of leaving the place where the tragedy happened. Mars can make sorrow spatially permanent. The room where someone died may still be needed for life support. The rover involved in an accident may still be needed for survival. The landscape outside the window may become beautiful and unbearable at the same time. That emotional weight can change a crew. This is another reason why the first missions must avoid unnecessary romanticism. Calling astronauts heroes is easy. Designing systems that do not require heroism every week is harder. The goal should not be to create legends of sacrifice. The goal should be to make survival boring enough that people come home. Boring is underrated in space. A boring oxygen system is good. A boring power supply is good. A boring launch countdown is good. A boring medical day is good. A boring return trajectory is one of the greatest successes imaginable. Mars will provide enough drama without humans adding more through poor planning. The first crew trapped forever would not need to be foolish. They could be brilliant, disciplined, brave, and unlucky. That is what makes the risk worth respecting. Disasters in exploration often happen not because people ignore danger completely, but because complex systems meet conditions that were underestimated, compressed, or considered unlikely enough to accept. On Mars, unlikely events have time to accumulate. A 1% risk repeated across hundreds of mission-critical operations does not feel small anymore. A minor issue in one system can combine with another minor issue somewhere else. Power affects heating. Heating affects propellant storage. Propellant affects launch readiness. Launch readiness affects crew stay time. Stay time affects food, health, and radiation. Health affects the ability to repair power. The circle closes. This is systems engineering at planetary scale. And Mars is the place where every diagram becomes physical. A line on a chart becomes a cable buried in dust. A block labeled life support becomes a machine with filters that clog. A timeline becomes people counting days. A risk matrix becomes a sound in the wall at 3 in the morning. That is why the first Mars crew may be trapped forever. Not because one dramatic monster waits for them, but because the mission is a web. The web has to hold while being pulled by distance, weather, biology, machinery, economics, and time. If enough threads hold, humans will walk on Mars and return with one of the greatest stories ever told. If too many threads weaken, Mars may not need to kill them quickly. It may simply keep them. There is also a quieter trap hidden in the science mission itself. Mars is not only a destination for human ambition, it is also a world that may preserve evidence of ancient habitability, old water, buried chemistry, and perhaps traces of life that existed long before humans arrived. That means the first crews would not simply be explorers. They would be visitors inside a scientific crime scene that has been waiting for billions of years. Every boot, drill, exhaust plume, leaking seal, waste container, and warm habitat could change the environment around it. That matters for science. It also matters for return. If astronauts come home carrying samples, dust, hardware, or biological material exposed to Mars, the mission has to think carefully about contamination in both directions. Earth life should not be carelessly spread across sensitive Martian regions, and material from Mars must be handled with caution when it returns. Planetary protection is sometimes described as paperwork, but for a human mission, it becomes physical design, suit cleaning, sample isolation, waste handling, air filtration, laboratory rules, medical monitoring, and return procedures. A crew trapped on Mars might be forced to break ideal scientific rules simply to survive. They may need to dig where they did not plan to dig. They may need to use local ice from a region that scientists wanted protected. They may need to vent gases, move contaminated dust, abandon equipment, or convert a carefully managed research base into an emergency settlement. Survival always outranks clean science in the moment, but the cost can last. A desperate crew can accidentally damage the very evidence humanity came to study. The mission can return with lives saved and questions made harder. This is another reason Mars punishes simple stories. The first crew is not only risking itself, it is interacting with a planet that holds scientific value, future settlement value, political value, and symbolic value all at once. A decision made to save oxygen today may affect research tomorrow. A route chosen for safety may contaminate a site. A rescue landing may scatter debris across terrain that was supposed to remain untouched. Even the rocket that brings them home has consequences. Its engines, exhaust, debris, and launch plume will disturb the surface. Dust lifted during ascent can coat equipment left behind. A launch failure can spread propellant, metal, and biological traces across the landing zone. The act of leaving Mars is not clean. It is an industrial event on another planet. That does not mean humans should stay away forever. It means the first mission has to know exactly what kind of footprint it is willing to leave. A human footprint is not just a mark in dust. It is an alteration of a world. And if the crew becomes stranded, that alteration grows. More digging, more waste, more emergency construction, more local resource use, more abandoned systems, more decisions made under pressure. The longer people remain unintentionally, the more the mission changes from exploration into occupation by necessity. This is a subtle but serious form of being trapped. The astronauts may still be alive, the base may still communicate, but the mission's purpose may have shifted beyond what anyone approved before launch. They did not go to become the first permanent residents. They did not go to turn a research site into a survival camp. They did not go to make emergency choices that shape the future legal and scientific treatment of Mars. Yet Mars may force those choices anyway. That is why every return plan is also an ethical plan. Bringing people home is not only about protecting the crew. It protects the mission from changing into something no one intended. So what would reduce this danger? The answer is not one miracle engine or one stronger spacesuit. It is a more careful architecture. First, the return system must be proven before the crew depends on it. That may mean producing return propellant robotically before humans leave Earth. It may mean placing the Earth return vehicle in Mars orbit early and monitoring it for a long time. It may mean sending cargo missions that demonstrate landing precision, power generation, dust protection, and autonomous maintenance. Second, the first habitat should not arrive with the first crew. It should already be there, checked, powered, stocked, and communicating. A crew should land beside functioning shelter, not beside a promise that they can assemble shelter fast enough. Third, supply should be spread across multiple locations, but not so far apart that reaching them becomes its own risk. A single lost cargo lander should not doom a mission. A single damaged rover should not trap astronauts at one site. Fourth, power must be treated as life itself. Solar power can help, but dust, seasons, latitude, and storms complicate it. Nuclear surface power may provide a steadier backbone, though it brings its own engineering and political challenges. A Mars base without robust power is not a base. It is a countdown. Fifth, dust must be fought from the beginning. Suit ports, external suit storage, dust-resistant joints, cleanable seals, electrostatic removal, hardened mechanisms, and habitat layouts that keep dust outside living areas are not minor comforts. They are survival features. Sixth, the crew must have enough medical capability to handle more than cuts and headaches. Surgery on Mars would be extremely difficult, but some serious conditions cannot be wished away. Imaging, pharmaceuticals, dental tools, telemedicine, training, autonomous diagnosis, and medical decision rules all matter. Seventh, mission planners must be honest about human limits. Exercise helps, but it is not magic. Training helps, but it does not remove stress. Crew selection helps, but it does not create machines. The schedule must include rest, privacy, mental health care, and realistic workload. Eighth, rescue scenarios must be designed before the crisis, not as comforting slides, but as actual hardware and procedures. Where can a crew go if the habitat fails? How long can they survive in the rover? Can another ascent vehicle exist? Can supplies be landed accurately near them? What happens if the return window is missed? Ninth, the mission must have the courage to delay if the return path is not ready. This may be the hardest requirement politically. The world may want the first human footprint. Sponsors may want momentum. Leaders may want history. But Mars will not become safer because humans are impatient. A launch delay on Earth may be embarrassing. A failed return from Mars may define the entire future of human exploration. Finally, the public has to understand what success means. Success is not a dramatic landing clip. It is not a boot print. It is not a speech. It is not a flag standing in weak, windless air. Success is the crew returning alive, or staying only because the settlement has become mature enough that staying is a real choice. Anything less must be described honestly. This honesty does not make Mars less inspiring. It makes the dream more serious. Mars is not a fantasy world waiting for human destiny. It is a planet. It has mass, weather, chemistry, geology, radiation, dust, seasons, and distance. It is not impressed by courage. It does not reward speeches. It responds to engineering, patience, and respect. And maybe that is what makes going there meaningful. Not that Mars is easy to conquer, but that it is difficult enough to force humans to become more careful than they have ever been. The first people on Mars will carry more than equipment. They will carry the reputation of every mission that follows. If they return safely, Mars becomes possible in the human imagination in a new way. If they are stranded, the dream may not die, but it will change. Every future plan will be haunted by the question of whether ambition outran responsibility. That is why Trapped Forever is not just a scary title. It is the central warning inside the Mars dream. Do not confuse arrival with victory. Do not confuse survival with freedom. Do not confuse a base with a home. Do not confuse a plan to return with the proven ability to return. Mars sits close enough in the night sky to feel reachable, but far enough away to expose every weakness in how humans think about exploration. We are used to imagining frontiers as places that can be crossed by brave people. Mars asks for something colder and more disciplined. It asks whether bravery can be supported by systems, whether dreams can survive budgets, whether life can depend on machines for years without those machines becoming prisons, whether humans can build a path home before celebrating the road outward. The first crew may stand on Mars and look back toward Earth as a bright point in the sky. They may know that everyone they love is somewhere near that light. They may know that every ocean, forest, city, childhood street, and open window belongs to that distant star. Then they may turn and look at the rocket that is supposed to take them back. That rocket is not just hardware. It is the difference between exploration and exile. If it works, Mars becomes a chapter. If it fails, Mars becomes the whole book. And this is the terrifying truth hiding beneath every beautiful image of astronauts on the red planet. The hardest part of Mars may not be getting there. It may not be landing. It may not even be surviving the first night. The hardest part maybe keeping the promise that the people who go there still have a way to come home. Because a human mission to Mars only becomes a triumph when the planet does not get to keep the humans who dared to touch it. Until that promise is proven, every footprint on Mars carries a shadow. The shadow of the ascent vehicle, the shadow of the launch window, the shadow of the supply chain, the shadow of the human body changing under alien gravity, the shadow of Earth, visible but unreachable. And somewhere inside that shadow is the question that began this half of the journey. Can you leave? The safest answer is not a speech. It is a rocket that has already been tested, a habitat that has already survived, a power system with backups, a crew with time to rest, a rescue plan that is more than hope, a mission culture willing to wait. Only then does Mars become something more than a trap. Only then does the red planet become a destination instead of a one-way door. And if humans ever do stand there, work there, sleep there, launch from there and return safely across the dark, the achievement will be greater than the first landing itself. Because they will have proven something Mars never wanted to give easily. Not that humans can arrive, but that humans can leave.